So good morning, everybody. A very warm welcome to all of you to this APCTP ISCS SNB or SNBOS National Center for Basic Sciences workshop on computational methods for emergent quantum method, from theoretical concepts to experimental realization. A warm welcome particularly to people who have come from abroad, both the speakers and the participants, and also participants from outside Kolkata. I'm sure this workshop will be extremely enjoyable and a learning experience for all of you. And this next, I think, 9 days, right, is packed. I'll just give you a brief description of the plan of the workshop. So we have 3 categories of lecture. The first category of lectures are tutorial lectures, and the duration is 1 hour 15 minutes. So 1 hour will be the lecture and 15 minutes essentially for discussions, right? So it has to be more interactive because you should make efforts to learn. That's the most important part. Second one is perspective lecture, which essentially introduces, because most of you are doing research, this introduces to a current topic in the area where such methods are applicable, right? And these lectures are usually of duration 1 hour. So 55 minutes lecture, 5 minutes discussions. This is more of a conference mode kind of a thing. And in addition to that, we have put a slot which is 1.5 hour duration, which is a tutorial session, where some of the lecturers will demonstrate codes if they have one, right? How to essentially implement these numerical techniques that is going to be discussed in this conference. And also this is a kind of an open session, right? You can catch hold of the lecturers, talk to them, right? Clear your doubts. And I'm sure, right, people who are in their initial year of PhD years, right, have tons of doubts which often doesn't get cleared up. So you have here a pool of experts who will possibly help you to clear up these doubts, right? So with this brief comments, right, I would now invite my co-organizer, Manoj, to take it forward. Yes, Manoj.
Good morning. Welcome to SNBNCBS Center. Also, I hope you'll have a nice stay here. I'll not take much time. Without delay, I'll request my director to have some few words for this conference. Please.
Thank you, Manoj, and very warm welcome to SNBNCBS Center, especially the friends and the students who have come all the way from outside India as well as within India but out of Calcutta. In fact, I'm very happy that this school is being organized. This was a long tradition of organizing schools at SNBNCBS Center, which late Professor Abhijit Mukherjee started. And there were many great schools, you know. In fact, I had a collaborator in Moscow State University, and I was just discussing why the Russian science is not really at the level which we used to see before. His answer was because all these great minds have left the country. I said, good enough, but the Russians are still the Russians. You know, you can still generate great minds. The answer he gave is very important. Because they left the country, the flow of knowledge stopped. The flow of knowledge is extremely important. And the schools are extremely important to facilitate this flow of knowledge. You know, because there are so many students in this audience who will be in future all the speakers and the people who will be on this stage. That has to be given from one generation to another generation. And I think the school plays the most important role in making this happen. In fact, there were so many SCRC schools, both in high energy and condensed matter, who played a huge thing. You know, my postdoc, the supervisor, Ole Anderson, was known for all his lecture notes, starting with Kanpur lecture note, which happened in IIT Kanpur. Because these were schools where people used to give lectures and then made some lecture notes out of it, where all the details will be worked out. So I am extremely happy that this has happened. And thanks to two primary co-organizers, the conveners, Manoranjan and Indra, took all initiative to make it happen. And also the topic of the school is very, very pertinent because you know there are a lot of focus now in worldwide given on quantum materials. And the world there is materials, so you need to actually be an expert who should know the material specific aspect as well as these materials being complex. Very often you used to use certain numerical models of these complex phenomena which can be handled. And two parts of the school, part 1 and part 2, they actually try to address both this aspect. And the perspective talks are supposed to bring the connection between these two aspects. So also the plan of the school is very well laid out. And I request especially the young friends, please take full advantage of it. And I will finish with one request to the organizers, if possible, bring out lecture notes. Because anyway, these are all being videoed. So you all know what has been said. For the speakers, probably it's not so difficult to write something based on it. If you make a lecture note, that will be a great, great contribution to the next future researches. So with that, once again, welcome, enjoy, and try to make best use of it. Thank you.
So, as procedure, we'll have as procedure, we have first lecture by Professor Harbola from IT Kanpur. Will take 1 or 2 minutes to rearrange.
I think you also have to tell about the change of switch.
Oh, so the first 2 lectures are by Professor Harbola, and third lecture will be given by.
So there's a switch.
So there is a switch. So please, and we are around to help you out.
And the lecturers will be informed, right, up 10 minutes before.
Yeah. So we'll be informing faculty to
Stop.
stop
No,
morning at 10 minutes, and then stop sign at completion of the time. And she will be taking.
I think just before I start, you made a very good suggestion that lecture notes be made.
Yeah.
I think all the workshops or centers like these who have these regular workshops, one should actually have a scribe. Because although, at certain stage, people do it promptly. And so I think from now on, I'm going to say there's a workshop. There's a lot of discussion takes place. And that is where real skill comes. This is going on.
No. This
will be separately.
So this they can see vaccines. They have panels.
No. What he is concerned about the online.
Lecture will be there.
Camera. Yeah. So
Okay. Okay, and then
So people here they can see this. Those who are on this
either. My guide. No, I can clear the papers.
Yeah.
Yeah, same thing.
No, can you put it like this?
Give me the
Not
color
like
wala.
color wala.
Certainly feel very constrained.
That's right. Hello, hello. Let me check. Sorry.
Do I need to wear this while giving it? No, it won't be there. Because it's shape. If it disturbs, then I'll take it off.
It's up to you.
Begin. Is it a signal for beginning of?
Yeah, so it's one dot.
Okay. Okay, good morning. First of all, I also wish to thank Indra and Manoranjan. They've been working very, very hard to organize this. And I hope they are able to do justice to what they have thought it should be like. So the first talk is on, so he said quantum materials. I'm from the quantum side. Okay, so what we are going to talk about is how do you do the calculations for materials with quantum mechanics, right? So usually, and most of you are involved in theory, density functional theory calculations, material calculations. So probably you've heard of Thomas Fermi theory, that was the beginning of the FP. Am I right in assuming that? Thomas Fermi theory? Yes? So I'm not going to start from there. What I'm going to start from, I'll straight away motivate you how you could have an orbital independent potential to do calculations, right? So, I'm not going to take that usual route. So, minimum we start with is artery. Of theory. Right, and this is a mean field theory. And what it does is, before that, I just qualify, since we are doing materials and we're not going to talk about magnetism for the time being. So I'm going to assume all my systems are spin compensating. All right, so spin right now I'm not taking into account. It can be taken into account, but right now assume that there are there's 23 electrons and all that. Now, when you do Hartree-Fock theory, right, this is to assume a wave function, a variational form of the wave function, which is a Slater determinant. All right, so I'm going to remove this S also now, just write T because I don't want to keep writing again and again. And you have wave function, which is 1 over factorial, and that is the vector that does the normalization. And then you fill in orbitals. Y1, X1. I'll tell you what X1 is. Y1, X2, and so on. All the way up to Yn, X1, Y, and Xn. Where X, now I do keep track of the spin of the electron. So X is the space variable and the spin variable. All right. And then you optimize these orbitals. Right? How do I do optimization? I do that through variation principle. And that is to say that what you do is calculate the expectation value of the true anybody having thrown here, and then say what orbitals minimize it. What should be the orbitals, right? So you take the expectation value, and I should write this clearly. And that expectation value is going to be and this you apply something called write it for the reference Frank-Condon rules that give you how to calculate the expectation value of this. It comes out to be summation over occupied orbitals. I may as well sum over spin. So let me write this as MS, just to make sure that this is a Z component of this is the kinetic energy term. This is fine. No issues. Next term is the external potential. I'm assuming a lot of things you know, so please stop me if I'm wrong in my assumptions. Then there is this term, the Hartree term, the Coulomb interaction of the density. There's one more term, right? And that's the term I want to focus on. And then plus the last term, which is a minus sign.
Sir, we are not able to hear.
R phi I R prime over R minus R prime is equal to epsilon R phi I. Yeah. Probably up to this point you have all studied, right? I mean, this is the equation, you solve it. So these are all fine. This is acting on phi I. So this is very nice. The only thing is that once you start doing it, and in all this, I'm going to assume we're doing a calculation on a grid. No basis set business so far that people will talk about later. So I'm after the exact solution. Somehow I'm solving this equation, right? And so when you do it, this is fine. You take the second derivative of this. This you multiply. This you multiply. This is a funny animal, right? This is giving an operation on the ith orbital, but in a non-local sense. It is acting on I at all the places. So it is like this term, right? This term was acting locally. So let me just write it and you see the difference. R minus R prime, phi I, R prime, d R prime. So it acts only when R is equal to R prime, right? Same thing with this. This acts all over, right? And that's the difference. And I can write Bx R prime is equal to minus summation J summation ms is acting on the ms orbital phi j star R prime phi j R over R minus R prime. Right? Any questions so far? Okay, so this is how it acts. Now this makes life a little difficult. You can think of it another way. You can think of also this term as I can multiply by phi I R in the denominator and in the numerator. And I can think of this, if I want to think of it as a local potential, as V x I R phi I R, where Vxi is equal to integral yj R prime star yj R yi R prime over I R minus R prime. So either you think of it as a non-local potential, or has a potential which is local, but then it is orbital dependent. It depends on which eye it's acting on. But this is actually not a very good way of looking at it. It makes sense only in this multiplicative sense, because if there's a node in this orbital, right, it blows up, right? So if there's a node in this orbital, and all this. So, for example, if I would plot it, right, Vxi, it do something, and suddenly blows up. Something, blows up meaning really blows up. This is YIR. We'll see. This is not a well-behaved potential. That when you work in metals, right, the Sommerfeld model or free electron model works pretty decently. Not exact, but very decent. Whereas if you do Hartree-Fock theory, I mean, you make your theory more accurate, right? So metals, there's a problem. What is the problem? CV E misbehaves as T goes to 0. Okay, then metals become ferromagnetic, or RS greater than some 5 or something, or some number. I don't know. Go to load and system, they all become parallel squares. Becomes better, right? Then bandwidths are too large. What I mean by that is you take the conduction band, which is like this, and Hartree-Fock theory becomes something like this. Then in semiconductors, the band gaps are very large. Okay, they come out almost double. If you've done those calculations, you'll see that. Okay. So there are problems, and so I just want to point that out. And just from this, you also want to understand. So this part, CV misbehaving, is basically because your E or epsilon K, okay, in a funny way, it has some sort of a singularity with respect to K at Fermi level. Okay, this you can read the details. Then this comes because after a certain energy, right, it's better for all of them to be parallel because it favors parallel systems. Bandwidth is too large because somehow the electron-electron interaction is being calculated in an approximate way. But if you really think about it, free electron model works stealing each other. That stealing is not taking place. In other words, what we call correlation in technical language is not being taken into account. Okay, and then a lot of people say band gaps are too large, and I just want to comment on that. And from this, you can understand why band gaps are too large. I just want to comment on that. So, if you look at the Vx, which I wrote as summation J ms, right? The sum over phi J r star prime phi J r, and this J is all occupied orbitals. If I add one more electron, right, I can is only occupied. If I add the n plus 1 electron, I add this 1 plus 1 electron and subtract it here also. Here I put a negative sign, add it. And you see this becomes like an n plus 1 part of the problem. I'm solving the same equation. I'm solving the same equation with this Vx for the n plus 1th orbital. And I can think of it by adding and subtracting the same term, self-retraction term. And that means if you're solving an n plus 1th problem, all the levels go up. The Coulomb interaction is more. So if the n problem was like this, n plus 1th give you something like this. This becomes the gap. It's large. Okay, because in a sense, when you're calculating see, Hartree-Fock is all about occupied orbitals. When you're calculating epsilon 1 plus the eigenvalue for the n plus 1 level, you're doing this. You're doing actually solving an n plus 1 electron problem. So you're overcounting. So the Hartree-Fock epsilon. That's the general comment about Hartree-Fock. But what I want to use this as a motivation for is, wouldn't it be nice if we could get rid of all this, right? And make our problem really nice. That's why I said I'm not starting from Thomas Fermi, I'm starting from the mean field equation Hartree-Fock. And what my goal is that minus 1/2 z square plus V external plus V Hartree plus some V local on I. If I could do that, I'm reducing the complexity of my problem, and hopefully, to a large extent, I'll also take care of it. Is the motivation clear? I want to make this a load. Is that okay? Any questions, comments on that? So let me just go historically. Okay, this attempt was made, and it was made by Slater. And what Slater said is, look at this, Vxi, right? If you look at Vxi, and I'm going to introduce all the concepts that we take over to DFT from here. It is minus summation, right? Phi j, all that. So j, ms, phi j star, r prime, phi j, r, phi I, r prime over phi I, r, mod r minus r prime. Now, this thing is orbital dependent. Let me just write in a slightly different form. Let me write this as minus summation some rho x I r prime over r minus r prime dr prime, where rho x I is summation ij ms star r prime phi j ms r phi I on phi, and this integrates to 1 over r. This is known as the Fermi orbital dependent Fermi hole. And the exchange energy or the exchange potential is the Coulomb potential that is corrected for because of this hole. Each electron is moving around in either orbital, the whole orbital. All right. Now, what Slater said is, let's make life easy and take the weighted average of this hole. So he defines something called the Fermi hole, rho x r prime, which is equal to summation phi I star r phi I r rho x I R prime divided by summation I star. This is the weighted average of this formula. Okay, orbital dependent formula. And this becomes orbital independent. And this has a very nice property that the exchange energy that we wrote earlier can be written as minus integral 1/2 rho r rho x r prime over r minus r. Prime. Yeah, prime. This is a local potential. And my equation becomes minus 1/2 del square plus V external plus V hard plus V exchange later. This becomes a very nice potential, local potential. So if you were to plot it on an atom, it behaves something like this. Okay, let's say this is 1 neon. R V exchange later. All right. And then he further said, let's approximate this by something called local density approximation. That I'll use the expression for rho x r prime, which is true for homogeneous electron gas. That is being calculated using plane waves, and this value comes out to be minus 3 kf r over y, where kf r is 3 pi square rho space. So you get something called the Slater equation. You further simplify it. Everything is in terms of the density, and you do your calculations. Okay, now what I like you to do is Google X alpha method. This is also origin of something called the X alpha method. This is the exchange potential. Then he said, let's put an alpha in front and make this parameter, vary until you hit the minimum energy, and you get X alpha. So happens alpha usually comes out to be 2/3. Okay, this is a setup that I can, through some method, get a local potential to do my things. Is that okay? Instead of all that complicated Vxi, rho xi, which is also not well behaved at certain points, you can get a local potential. Any questions so far? What should I have done? Now this is modern. He did an approximation doing this. What I should have done if I really want a local potential. That's Hartley form, right? So next question. What would I do that the true local potential? Like a few comments on this. What should I do? This is a very nice physical way of doing it. But mathematically, what should I be doing? What should I be doing variationally? Let's put it that. There's nothing wrong or right. Just let your imagination go wide. Comment. What should I do? If I really want a true local potential that gives me Hartley Fock level accuracy. I have no water gun, no gun in my hand. You can answer, and I'll say at most, or maybe I should do this. But say something. Let your imagination take over. Do interaction. Do what? Coulomb interaction is being calculated through an exact expression. Right? V Hartree, I'm calculating through an exact expression for the potential. I'm looking for a local exchange potential that would give me Hartree-Fock level accuracy. So what I would do back to variational principle, right? So these orbitals I are coming from an equation like V external, V Hartree, plus some V exchange. Let me say that there is an exchange local potential. What do I do in Hartree-Fock theory? Usual principle. I make these phi i's parameterize. I put some parameters there, right? And minimize the energy, isn't it? Let me treat this as a parameter. If you like thinking in terms of numbers, what I'm doing is, or numerically, I'm solving the Schrodinger equation, right, on a grid. And at each point, I'm giving some value to Vx. Some value. And vary these values until the energy becomes a minimum. So in a way, I'm doing a, whatever, n parameter calculation. How do I do that? I have the expectation value of V H Hartree-Fock, and I do this. I do everything is depends on V. Whatever V external is fixed, this is coming from orbital, so this I can calculate. I want to keep varying this until these give me the answer. Okay? And this is known as the optimized or the OB. Regular orbit, which is what top of the conduction band is same as the Hartree-Fock. Not only that, the densities are the same. I'm putting this plus sign, now equal sign, almost equal ppm levels. So what lesson do we learn from here? The lesson we learned, it is possible to come up with a method in which I'm solving Hartree-Fock problem, but with a local potential. The fact that I can plot this potential, right, is itself quite an achievement. Instead of having for 10 raised to 23 electrons, so having all those potentials, I have one single potential. Okay, and this if you want to come up with accurate calculations, it's mathematically demanding, numerically demanding, it gives you very good answers. The moment you take care of this as a local potential, all those problems I told you about, band gaps come out all right. Bandwidths are okay. Okay, so it is possible, and you see this. It is possible to do an interactive electron problem with a local potential if formulated correctly. So let's conclude with this, that what I have shown you at Hartree-Fock level, I can do the same problem with a much less complicated, very simple looking potential, and gives me correct answers. Any questions, any comments so far? Yes.
Does the Hamiltonian or energy conversion is unique solution by parameterization?
Yes, whenever you are minimizing, it becomes unique. I'm finding the minimum solution. Okay. Except for a unitary transformation. But anything else? Whenever you do, I'm basically doing a variational principle. It's just that I've chosen my parameters to be different. I'm treating the potential itself as a parameter.
So while calculating this, we do this using like.
It's a numerical technique. Yes.
Yeah, single particle density function for all the other calculations. That is called the Coulomb part and all of them.
Yeah, so whenever I do that phi I, right, I'm getting the density. Once I have the density, the rest of the terms are easy to calculate.
Yeah, so when I try to minimize my energy, that means I'll have to look at something like I have to parameterize my single particle density with that parameter.
No. I am actually taking some arbitrary potential, solving, getting my phi i's, right? Getting my Hamiltonian expectation value with respect to the Slater-driven form from these phi i's, then varying this until I hit the minimum.
So it's some function of R only.
Function. This is a function of R, and as I said here, any function of R you can think of a function of n variables. If you're doing a grid graph.
So can we do something like this, like for all, like we can think of this potential as similarly like Coulomb potential and try to find the corresponding row for the exchange potential. Can we do some reverse technique like that for that material?
What you're saying is, can this potential be thought of as arising from some sort of a
Yeah,
exchange role? Yes, absolutely. Yes, the whole physical interpretation. Okay, but the idea I want to drive home, but very good question. I want to drive home is, so it comes out from this exchange role, except you have to do two more steps, right? Okay, so Slater was not exact. It overestimates, OPM is exact. So the point I want to drive home is that you can do a calculation with a local potential. Is that okay?
Can I ask a question? So OPM essentially involves that this expectation value of the Hartree-Fock Hamiltonian.
Yes.
You're taking up or doing a variation with respect to a non-local potential.
With respect to a local potential.
So Vx has been transformed to a local potential.
Yes.
That in the sense of Slater or
In the sense of, yeah. So I assume these orbitals are coming from a local potential.
okay.
I calculate the expectation value. Then I do some mathematics and come up with an equation for this potential, which I solve.
And historically, this was known to Cohn and Cham.
This was, the Sharp and Horton did it in 1950 something.
Okay.
All right.
So
The first solution came in 1972, which is post Cohn-Cham, and then immediately it was recognized this is Cohn-Cham potential.
Sir, video is again gone now.
gives me psi, it becomes a functional. So let me write it like this. It's a function of this R1, R2, and so on, and it's a function of O1. Okay? And therefore, I can write the energy, which is psi, kinetic energy operator. This is an advanced workshop, I just keep writing this. The external plus the electron. This is also going to be a functional of rho. Okay, and then the variational principle. Is delta, the functional derivative of E. Whenever you do variation, you keep the external fixed. Otherwise, you'll be changing the system. You keep the external fixed in that system if I vary the density. Right? This is 0 with the constraint that integral R dr is equal. And when you put that constraint, I can apply that constraint with the Lagrange multiplier, and therefore this is that okay? And therefore, mu has an interpretation. Delta E, if I now allow a general variation of the density, delta rho dr will be mu delta n. So mu is the EDN, is B external. This implies mu is MS. That is the essence of Mohn-Burke theorem and the corresponding variation principle in terms of the density. Is that okay? Any questions so far? Okay. And chemical potential, since we're doing material, right, in terms of the extended system. So if I were to make a band diagram for an extended system, I'm taking something which is filled conduction band and also something where conduction band is half filled, all right? The chemical potential is the change in the energy when an electron is changed. So this is E equals 0. This is, in this case, this is mu equals 1. Right? Although bands are made in single particle picture, nonetheless I'm just making this. So in a single particle picture, this is becomes like removal, otherwise it is equal to the ionization potential, the minus sign.
So why are you drawing in reverse order? Like EC, VO and EVO?
Valence band, conduction band is, because I was being stupid. That's a simple answer. Sorry. Yes.
you assume the external energy, the
External potential
exchange
is
energy.
fixed, is fixed.
I think you consider the exchange energy is the external potential, right?
No, exchange energy will be in VEE expectation value. When I take the expectation value of the electron-electron interaction term, exchange, correlation, everything comes there.
But you just now said, right, like, we can take like a local potential, like for interacting electrons,
Yes.
we can convert it to a single external.
No. So
potential,
there's a difference. When I convert that, I'm solving this problem, right? Plus all that exchange. Here I'm calculating the expectation value. This is the true interacting system. That I'm trying to replace that by a non-interacting system. That is the difference. I switched gears. I erased that part.
Okay. This is like the original form.
This is the original.
Oh.
Okay. So, all right. So this is the ionization potential because mu, as I said, is delta E, delta Z, which is equal to delta E divided by 1. If I remove an electron, energy goes up, right? And you get minus I. Okay? That's the mu, that's the chemical potential. Now, I can do the same thing. Now let me ask, and that's the last thing I'll do in this lecture, and then we stop. Let me ask, can I write this equation delta over delta rho E external rho equals mu in some sort of a non-interactive problem? Okay, so assume there exists a non-interacting system that gives same density as the interacting system. That means I'm assuming, and I have already motivated that can be assumed, that is square plus the external plus some V extra, right? Whatever it comes to Hartree exchange and all that. Some V, let's call it, what do you call it? Let's call it V effect. Yi equals epsilon. Let's assume there exists a system like this, right? Then, which gives the same density. Okay? If it gives the same density, as the interacting system. Now let's see. What does this amount to? This amounts to delta by delta rho of expectation value of T. Everything is a function of rho now, right? Plus V external plus V Hartree plus delta E, what I'll call exchange correlation. This I've already motivated. This is part of that. Is equal to. What I'll do in DFT, this T rho is equal to expectation value of the true energy operator with respect to the true wave function, right? I'll rather split it. I'll take out a part which I'll call the non-interacting kinetic energy of the same density plus all this plus delta EXC DFT. I've done a trick. For a given density, the two kinetic energies are going to be different. Right? So I absorb the rest of the part of this. Right, where XC EFT is EXC quantum mechanical quantum mechanical plus E minus TS. Okay. Now notice this is V external, or this is V part 3, or this is also depends on only on R, and this is called V exchange correlation. So I've written the Euler equation for the density, right? This is a variation of density. So the Euler equation in terms of non-interacting density, because this TS is non-interacting. But this is equivalent to solving this equation. Where summation I phi r square r gives you rho r, and by construction mu is the same. For the non-interacting system, the removal energy will be from the highest occupied, so epsilon I max is going to be you understand what all I did? I replaced this whole thing. I did a mathematical trick. Replace this T by Ts, absorb whatever the difference is exchange correlation, right? And then I found that this by Moonberg theorem, this is a unique potential, and this is equivalent to solving a non-interacting problem, right? So I found a way of doing a non-interacting problem that gives me the same density. And this not only gives me the density, it also gives me epsilon max by construction. By construction, we have the mu has to be the same. It's the same system, right? So this has to be mu, which is minus I. So if I solve this problem, I should be getting the correct density, the correct exchange, correct epsilon max. And from the density, if I put it in all this, I get my energy. That's the whole methodology. How we employ it is going to be the topic of next section. I'll review Ponchak, and then all those functionals are developed. That will be taken over. Okay, I stop there for time. Thank you.
It's time for questions. Or otherwise, Manoj will start asking questions. Go ahead.
I think we continue on T also.
Yeah, but yes.
Is there any questions right now that others will also benefit? Any comments, questions?
The students don't have questions, let me ask.
Of course.
So, did I understand correctly that you motivated Ponchak without invoking Westberg code first?
That's right.
From OPM,
Yes.
OPM, right? And for a formal proof of the Westberg code theory,
Yes.
for E-generate grounds, you need the constraint search approach, right? What you
Not
say-
necessarily.
Not necessarily.
Not necessary. Not necessary. Then even now, what you do, okay, so since you asked, what you can say is that now I have a set of wave functions, psi 1, psi 2, that are all giving me the same energy, right? So I restrict my search to V external that give me a set of wave functions that give me the same energy. Then the proof goes through. It's slightly more clear. You don't need to. Consider it very easy to think. It's a very nicely done in Brazil course.
Yeah, surely.
Maybe students want to ask questions, so that's why I asked for them. So I think maybe it's easy to question whether your assumption that you have made is the density can be represented by some of non-interacting wave functions. So what then
Okay.
representability?
So
That part,
yeah, I did not want to go into that.
yeah.
This is when you assume this, right? When you assume this, you're assuming something called the non-interacting end representability. That means density of n electron system can be represented by a non-interacting system. And this is a problem which we assume it is so. In fact, you will find systems, one or two I carbon probably where you don't get it, but you assume. Yes.
Yeah, I know it's a tricky question. So are you going to address that?
That's why I know emphasize this.
So some of the so-called strongly correlated electron
Yes.
systems. Yeah,
But even
there are some
non-strongly correlated carbon. That's
Yes.
sure.
Yes, there is a question from.
Yes.
So when you're solving.
Bit louder, Rohan.
When you're solving these variations.
I think the
Yes.
microphone is not on.
So when you're solving this using variation principle, how do we ensure that the final wave function that we're getting that has antisymmetric properties like state
Oh, so when you do apply variation principles, you construct only those wave functions that are antisymmetric. That you enforce from outside. It's not going to be automatic.
So
Antisymmetry is an additional requirement for it being a polynomial. That's why either I choose later determinant, or when I do variation principle, my size which I chosen are antisymmetric.
So you're saying that initial cases we take.
Antisymmetric, yes, it is very antisymmetric.
So after applying variation principle, the antisymmetricity should retain.
Yes, it will retain because that's how you construct it. Like for example, why did I write slated determinant rather than just a product wave function? That is to make sure that it remains antisymmetric.
So is it a necessary condition to choose the antisymmetry system? We can do it for boson system as well, right?
Yeah, do it. Prospectivity equation.